We're now going to put all the pieces that we've been learning in the previous videos together and talk about what happens as we add a certain amount of heat or release it to a mass of water. And we're going to plot out the trajectory of this mass of water on this graph that plots the temperature of the water body versus the change in the amount of heat that's added or released. And when we add heat, we're going to be moving this way on the plot. When we release heat, we're going to be moving this way. So let's start with a chunk of ice only. So a solid here, ice only. As we're some temperature below 0 degrees Celsius and we're adding heat, and we see that there's a linear increase in the temperature of the ice from maybe negative 40 degrees Celsius at an initial temperature, and we're warming it up as we add heat. At a certain point here, namely at 0 degrees Celsius, we're going to hit this temperature when something special happens. We keep adding heat, but the temperature of the ice actually doesn't change. Instead, it starts to melt. And as we're moving along here, we're adding heat, and at this point in our plot, we've got something special where there's both ice and liquid water together. So we're adding heat, we're not changing the temperature of the ice, but instead we're causing it to melt. We can go along here, and when there's just a little bit of ice left, it finally disappears and it's all liquid. At that point, this body of water can start to increase in temperature again. And so it's going to be rising and rising and rising and rising here. And at this point, we just have a liquid water. We're adding heat to it, and we're increasing the temperature. When we hit another special point on this plot, 100 degrees Celsius, or the boiling point, we now have a bunch of liquid water, but we're starting to boil it off, and so we now have liquid and gas together. And we're going to add heat, 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 but we still have a little bit of liquid left. And you'll notice that I'm going to draw this horizontal line up here about 6 times longer than the length of this horizontal line. That corresponds to the much greater latent heat of vaporization compared to the latent heat of fusion. So we're adding heat, we're adding heat, we're adding heat. Finally, there's just a little bit of liquid left. Most of the water is in the gas phase, and we're finally getting rid of all of that liquid. Once it's all a gas of water vapor and we continue to add more heat, we're going to see the temperature again start to increase in the gas. And we're going to have gas only, or vapor, water vapor. There's a few other things that we can note on this graph. If I define M as the mass of water that we're considering, and remember that C is the specific heat, let's let delta T be the change in temperature, or equivalently a certain distance on the y-axis. Delta Q is a certain distance here on the x-axis, and we'll let delta or lambda V be the latent heat of vaporization, and lambda sub F be the same but for fusion. We can actually draw some more things on this plot. For example, this distance here is equal to delta Q, which is equal to the mass of the water body times the latent heat of fusion. If we consider this slope, the rise over run here, when we're just warming up this liquid water, this is equal to delta T over delta Q, which is equal to 1 over the mass times the specific heat. This distance here, we have another delta Q, but this time it's the mass times the latent heat of vaporization. Finally, we can draw another slope here, another rise over run, another delta T over delta Q, which in this case again is just going to be 1 over MC. It turns out that if it's a liquid or a solid or ice, the specific heat stays the same, whereas the vaporization temperatures change. Now, there's a bunch of take-home points that I can summarize with this plot. One is that when you evaporate or boil water, it takes a ton of energy. It's a really energy-intensive process relative to how much energy it takes to melt water. Two, when you actually go in this direction, when you are condensing water, that's actually releasing heat. And as a result, that's the reason why, if we remember back to the last video where I said that moist adiabatic rate was not quite so high, it's because as a cloud is rising and it's raining out, heat's being released. And so the change in temperature with elevation is not as extreme as it would be during the dry adiabatic lapse rate. So those are some things that we can glean from this particular way of looking at the relationship between temperature and heat for a body of water.